preconditioning. There's a 93% humidity environment at a temperature that's appropriate. It's flexible. I suppose when you take it out, you don't want a lot of condensation. So you would set that to be, the equipment should be warmer than the room, right? So if the equipment came out colder than the room, you'd get condensation. So you kind of set that so that it comes out. You know, if you're a big test lab, you've bought this walk-in chamber and it's a 2-room deal. You know, the room you come out of to do the leakage and dielectric is actually at the exact same temperature as the chamber. You know, there's ways to spend all sorts of good money. But generally, you're not a 2-room chamber, so you just set it to be a little warmer, right? If I'm right. So if you have the IP, ingress protection, we didn't talk about it. It's going to be when we talk about liquids in the last session tomorrow. But there's an IPX 0 for nothing. And we do a 2-day test, humidity. But if we go into the IPX1 or all the way to 8 immersion ones that drip, we actually end up doing a 7-day test. That's what the standard says. This 93%. All right, so they come out and they get a dielectric and leakage. We generally do the leakage first and then the dielectric. All right, leakage is a bit complicated, and I see time-wise I'd like to be finished. So I'm going to risk going too fast. But here's your standard, organized, you know, format-wise by me, but the text is correct. These are defined terms. So leakage current's a big word that includes a lot of subwords. And so earth leakage is from the mains conductor. Current in the mains earth conductor. Touch is from surfaces, or surface to earth or surface to surface. Normal single fault. Excluding patient connections. Patient leakage is from the applied part, so various points would be patient connections of the applied part. So that's always a patient connection to earth. And patient aux is point to point, whereas touch included both of those ideas, point to earth and point to point, but on accessible parts. But once we get into applied parts, we have a special leakage current word. So that's where all these words come from. This is the applied part kind of words. These are the touch surface kind of words. Accessible parts, to be correct. All right, and if you want to think about it in a big picture way, the earth current's on the conductor. The touch could be to earth or surface to surface. The patient leakage is to earth. It's mains on the patient into the equipment to earth. That's that F type. It could be total patient leakage because there's more than one applied part. We're going to measure both together to earth with a slightly higher limit. With mains on the patient, we're going to allow it to flow back through both applied parts together, because aren't they on the patient together? And we're going to allow that to leak to earth. Patient aux is point to point. Okay, and I've shown a person because I want you to, you know, when we do the measurement, it's a meter or a measuring device box. And I want you to see that it's all about the person. All right, so 873 was referred to by the 842 that we looked at, both expressing limits for current. So D talks about Earth being limited to 5 million and 10 million single fault. So if we were permanently connected, these would be our limits. When we're cord connected, we actually open the earth. If you had 5 milliamps on your earth conductor and you open that, you'd have it from an earth touch surface to earth, and that's touch leakage. And that's limited to 0.5 in single fault milli. And so this has to be 0.5 milli if you're cord connected. And that's kind of in a note in case that wasn't obvious to people. I think with Amendment 2, they kind of added the note to remind people of that. But what they chose not to do was have a section for both cases, which would have made it even more idiot proof. Oh, I suppose this is the note. All right, C is the 100, 500 for touch, and A and B is the patient leakage stuff, tables 3 and 4. And we've sort of looked at these, so I'm kind of flying through. Here's your table 3 and 4 from B. Here's table 3, patient aux. So here's our 10 and 50 normal single fault. Here's our 10 and 50 because it's DC. So DC, we have very low limits. We think there could be cell necrosis. Now, if you look at the latest reference standards, that would not support these limits. 2 milliamps would probably be supported by newer research, but the standards retain these conservative values. AC, we have the 100, 500, 100, 500, CF, 1050. Patient leakage, same stuff, okay? Now, external voltage on a SIP-SOP. If we don't specify what's intended for our SIP-SOP, we put mains on there and it's normal. And we could still introduce another single fault, okay? So generally we're not doing this test because we're specifying our equipment on data ports. This is still table 3, total patient leakage. So in the case of single fault, they double. Is that right? So this should be, say AC, this should be 100, 500. Yeah, in the case of single fault, they double. In the case of normal, it's 5 times the single applied part limit. But with single fault, if you were 5 times the single fault limit, because it was 5 applied parts, for example, you'd run into trouble. Okay. Patient leakage, now we're into table 4. External voltage on the F-type applied part. So this test we love to do because it's F-type. And there's our limits we talked about already, 5 million 50. So CF has the 50, similar to the single fault, and BF has 5,000 micro because it's such a hard case, I guess. If you think about a big surface area for a heating pad, this would be a practical limit. And this is metal surfaces that aren't earthed. And that's not allowed for CF equipment, but we would allow it for B or BF. We'd put mains on that surface that's not earthed, and we'd make sure it's not going to couple to an applied part and cause patient currents, okay? Generally, if we had earth surfaces, we would earth them. But if you didn't, we'd do that test. Table 4, allowable values, total patient leakage. This is the F-type, mains on the F-type. Same limits. So total patient, we didn't see the 2 times. Oh, yeah, it's 2 times here. But not 2 times here, okay? 1 time still. And yet it's total patient, all the applied parts together. All right, so the gray is what we know and love, and the DC or whatever other situations, they're all here. Now, there's those body contact scenarios, surface to earth, surface to surface, mains on the applied part, touching a surface, the applied part. Mains on the patient, patient touches the applied part. Or the SIP-SOP, or the unearthed surface. So this is that person. So here's the 2 points, and here's the 1,000 ohms, and this is 10K and 15 nanofarads. And we actually measure this voltage, and we always divide that voltage by 1,000. And if you think about higher frequencies, that's not technically 1,000 looking in here, but at lower frequencies it is. So in effect, we have two things. We have the apparent current that we've calculated, and there's a reality current. And it's the apparent current that we calculate that we compare to the tables. So that frequency response for that model there, the filtering, means that every decade that you change the frequency higher, it's 1/10 of the impedance. And so in effect, you're allowing 10 times the current. But ultimately, you can never exceed 10 milliamps because of a burn hazard. So we do two measurements. If we think there's some high frequency going around, and that's why it's nice to do these measurements with a scope, we have to take a pure resistor and measure between the 2 points and measure the voltage, divide by the true 1,000 it is, and then we know the true current. And the true current must always be less than 100 milliamps. So this one will tell us, oh, sorry. Oh, this one will, never mind. When you do it with the figure 12, there's that trick going on. But as long as you comply with the table, you were within the limit. The limit being, say, at 10 kilohertz, that there was really a milliamp, and yet you calculated 0.1. Yeah, okay. It's 10 times the limit because it's 10 kilohertz. But anyway, it looked like 0.1. And then here you're going to measure it, and in fact, it was 1 milliamp, but the limit's 10, et cetera, et cetera. Anyway, you don't have to know that. I'm confusing myself. Know that when high frequencies are involved, you should be doing the measurement twice, once with the figure 12 and once with a pure resistor. Okay. And when you plug your equipment into a mains, you need a means to add 10% voltage. You need a means to reverse the polarity. You need a means to open one supply phase. And you need a means to open your earth. This is S7. This is S1. This is S5. Okay. And if you had a functional earth, you'd have an S10. So this tends to be a power source that you would plug into the normal mains and then have a variable voltage, maybe even variable frequency. So you could have 60 hertz. In Europe, that would be relevant. 60 hertz is worst case capacitive coupling. And then these switches tend to be a box that's within a leakage meter or just a box with switches for the pass-through mains. If you want to apply mains to a surface, you need an independently derived source. There's no real current here, so it wouldn't have to be big, but you need to be able to reverse this polarity independent of this polarity, which is the mains. And then that gets applied, and it's 10% rated. So you can buy nice power sources with the voltage frequency you want. You never want to test it on an American center tap to 240 or in Canada. And because the currents will cancel. And so worst case, you have to make sure you have a true 240 to earth. In fact, 264. And then you can buy from vendors the leakage current. So they have the switches, they have the figure 12, okay, they have the pure resistor if you're buying the whole the true capability you need. Make sure they can do the F-type applied part if that's applicable to you. That can cause a lot of leakage within the meter, and some meters aren't compatible for that. The meter will be in parallel with your product, and you'll get a lot of current if the meter's not suitable. You can make your own stuff. So this is figure 12. Here's your 2 points. Here's where you hook up your voltmeter, in this case, right to a scope. You can have your figure 12 and your 1K. Put it in a metal box that's shielded. You can build, pass-through switch boxes. You can build a little isolation transformer and mains on other surfaces. So however you do it, when you're doing production testing, earthing and leakage is part of 100% production. Of course, you're going to buy commercial equipment, and there's programmable equipment, logging equipment. So you're going to get all that fancy stuff. But for your validation or verification department within the research and development, you might want to have a nice flexible approach, and it's not going to be a pre-programmed approach. So with test labs as well, needs to be more manual. All right, there's normal and single fault. The idea is the same as what we saw in clause 8.1. If you open a phase or a protective earth on a cord connected equipment, those are single faults, and you can only do one at a time. But if you reverse the polarity of your mains, that's normal. And so you could do something normal with a single fault, that's a single fault. And you could reverse the polarity, that's still normal with the same single fault. Or those single faults, they'll have to be normal. And both normal, reverse, and normal would be 2 examples of normal. So leakage is done after humidity, but also after temperature. And in fact, we do it after especially accessories that are sterilized. We're doing it after that. One fall at a time, you're checking for your limits. Here's earth leakage. There's your earth conductor. The measuring device is right in there. This is the equipment under test. Here's touch. So you want to measure with the earth open, a touch surface to back to your supply reference. So with the earth open, it's no single fault. So you check your single fault. So with the earth closed, most of the current's going to stay on the earth, not much going through 1,000 ohms. But surface to surface, you're checking as well. Yeah? If you didn't specify your SIP sub, you'd be having mains on there, but of course you would. Here's mains on that SIP sub, and that presumably your commercial vendor would do that for you. Patient leakage. Now we need to know where our applied part is. That's what this is. We're going from applied part to our reference, earth. Oof. And so for leakage, we do that. And then think about mains on the applied part. So you'd have your independently derived mains, and you're going to put it on the applied part. Check your normal and single faults. Patient aux, so across your applied part, if you will. And there's an NX, is it K and maybe E, that talk about the kind of combinations you should think about. If you have multiple applied parts, if you had separate BFs and CFs, you'd do those together separately, all the C's together and all the B's together, not all of them. And then you check for those limits. That's just how it's specified. And so you do those separately if you had B. And so this is an example. There's a switch box and a scope with a measuring device. You've got meters to monitor your mains and things like this, yeah? In the test report, you're going to have a big table. This has been filled out for earth leakage, ER. And there's normal and single fault. So there's 4 cases. The only single fault is to open uh, um, oh yeah, S1's been opened for both polarities. Here it's closed for both polarities. S1's the phase conductor. And with touch, you're going to have 6 cases because there's an S1 as well as an S7. So here S7's closed, but S1's open. Here S7's closed, or the other way around. I don't know what 0 and 1 is. I'm losing it. S1 is, I think, open is one. Anyway, you can see why that'd be 4, and then normally you'd have normal in reverse with S1 and S7 closed. So 1 is closed. 0 is open. That makes sense. 0 for off. Sorry. And then now you've got those 6 cases, but you have a lot of surfaces. And so sometimes you've got this kind of surface, that kind of surface. So every time you have a surface, you're going to do 6 measurements. Okay. Here's your patient leakage, same 6 cases from each surface or surface to surface, if you will. This PM is our abbreviation for mains on the applied part. Okay. You've got 4 cases because the mains on the applied part's already a single fault. So we only do normal things. So we could do mains reversal and we could do applied part reversal. So there's 4 cases for each surface. So that's one table with all those cases. And so the limit could vary depending on which tests we're doing. And so there's a max. There's a measured, and then in remarks, we might put, actually, there's a header for each section where we can put the limit. But here I've shown the limit's been specified in the remarks. However you want to do it. So the test report will have all that data. And it would be the before humidity where we've had equilibrium, thermal equilibrium, and then after humidity where we're more worried that it was in the chamber for a while, and then we took it out and did the test. And so you've got all that data both before and after for all those cases. Okay. Questions? Because otherwise I'll move on. So the advice I would offer is leakage current, you know, and I went through it pretty quick. It must be pretty complicated, you're saying to yourself. No, you need to just take a methodical approach, slow and steady, thoughtful, methodical approach, and it all comes together. Yeah. Greg, do you have any advice about leakage current? Greg, I know does listing.
Hey, how you doing, Frank?
Good.
Yeah, I was a few minutes late this morning. I had to chase my dog through the woods. But other than that,
he saw the Easter bunny.
Yeah, I think so.
Did he get him? Maybe he saw Rudolph.
Yeah, I think he saw something out there. I don't know what it was, but he was gone in a flash. So I hunted him down.
Flying reindeer.
That last slide you showed there with S7 in the 1 position. Yes. The key in the standard, right? It says class 1 equipment only measure with S7 open and S1 closed under all possible conditions, right? So we do want to open S7 at some point in this test sequence. Is that true?
No. So, well, you could, but then what are you going to leak to? So what's ironic is having the earth intact is actually worst case, because now you've got a sink to the source. You know, you got mains on the applied part, a source, and it's looking for earth. So if you take the earth away, it's not really going to be able to leak through the product. Right. You know, it could be laying on their surface. You might still have that. And you might get some leakage, but so in the convention here, and I'd sort of forgotten, but 1 means closed and 0 means open. And so 1 is normal condition. Now you've put mains on the applied part, that really is a single fault condition. You know, the standard calls it a special test condition, but no, I think the standard's clear that you're not allowed to open the earth.
Oh, yeah, you're right. Yeah, you know what? I looked at the patient leakage, figure 14 that says that note I was just referring to. Sorry.
Yeah. So normal patient leakage, you definitely do both cases for her. Yeah, because you don't want you're taking away the opportunity for the leakage to go through the mains connection, taking that away. You're allowing an opportunity for it to all go down the patient who's earthed, and you're verifying that that's not going to be an issue.
Yes, absolutely.
So, no, for patient leakage to earth, with the patient normally earthed, that's okay to open the earth. But when the patient's at mains, that's a single fault. So that's the common sense way to think about it. And then, like you do, you read the text in the standard, but it's also good to know, well, here's what I think the standard's probably going to be saying. But yeah, you could be wrong. So that's why you read the standard. But in fact, that you'd be right in this case. All right. And what have you found? Do you have a commercial leakage meter, or do you do your own thing? Or
well, we have the oscilloscope version in the figure 12 circuit.
Yeah.
And then I have a Hioki leakage current tester as well.
Oh, okay.
But the Hioki is a great tool, but I found myself having to verify the measurements with the scope because it's flying blind somewhat. You don't really know.
You don't know whether to trust it, and that happens so often. It's always so nice to be able to do a test two ways. Agree. How often do they not agree? Yeah, why do they do it two ways? But anyway, okay.
But it's handy tool. The Hioki or that type of instrumentation is handy in the right hands, but I think it could be dangerous as well.
Yeah. Well, they're great, aren't they? You just hit a few switches, and everything's. But if you think about the prep, you're still hooking up all those cases, and then the switches go through their thing, or it might be multiplexed, So for production, it's important to kind of sort that out in an automated way. I would certainly second. But in verification activities, maybe it's important to be flexible and kind of looking at things and kind of learning as you go, seeing what's really going on.
Yeah, sometimes with the scope, you get a physical look at what's happening or where the leakage is coming from, and you can, isolate different current sources because you'll be able to see those other than the mains frequency. So.
Yep. All right, good. I think that's great feedback. All right. So let's talk about dielectric strength. Again, you're going to want commercial equipment, right? Because we've been talking about 1,500 volts. A lot of times we're talking about 4,000 or 3,000 volts. So where's this voltage come from? It's a nice commercial piece of equipment. You put that on the insulation that you're stressing for a minute. And you don't just apply it, bang, you ramp it up for 10 seconds. And, you're kind of putting that across a capacitor, a power plane and an earth plane. It's a big capacitor, even though it looks like a product that you designed and built. And so, mains and secondary, they're two capacitive plates. And so you ramp that up so that it can kind of settle in, with the charge, if you will. And then you apply that for 1 minute, and you don't want to see an avalanche of current. Now, there'll be a little leakage, if you will, want to call it that, because of the 50 or 60 hertz that the test equipment is. Now, you are allowed to do a DC test at 1.4, square root of 2, like a sine wave thing, the peak. So if you had a 4,000 volt test and you wanted to do 64, that's your math for the square root of 2. You would apply the DC for a minute, and you wouldn't have that leakage. But that leakage isn't a negative thing. You know, you might get a false negative, but with the DC, there really wouldn't be any. And so if it was going to break down, you'll see that as an avalanche. The meters shut off. If the meter sees too much current, they shut off. And that's an adjustable setting. So you could set that at 5 milli or up to 15 milli. So you set it at kind of the lowest that would give you nuisance trips for the safety of the tester, the person testing. All right, so this special test equipment on the production side, you'd buy the ones that are programmable with leakage and data logging, whatever else you might think is good. So line to earthing can work kind of in a black box way. You need to think about what switching is going on here in your mains. You need all those switches closed. There could be some energized relay things that need to be thought about. But in any case, all the mains areas to earth need to be tested. So sometimes you can do it in this way at say 1500 typically for 240. And with SIP-SOP, that won't work. Definitely probably won't. You'll get false negatives. If you think about it, you're trying to test this for 4,000 or 3,000. And what happens is the secondary is tied to earth, and there's a Y capacitor here. And so this is in parallel with this. And this is one means, because if this broke down, you have an earth, and the person touching it won't see a lot of current because the fuse is going to open. But here you don't have that. Here this could open, and so you don't want that to break down in a two means kind of way. But here you can allow it to break down in a one means kind of way. And so by testing this with all this hooked up, you can't test it because you're overstressing this. So to test a transformer or an optocoupler, you really need to pull that off the board and test just the component. So if your power supplies have already been tested, that's been done. Optocouplers, relays, whatever is here needs to be pulled off the board. Or you know, if you can pull the board off of the chassis and accomplish that, great. But you might not be able to. Even then, you might have this parallel path. Okay, so means to SIP-SOPs is you need to think through any possible parallel path stuff. All right, and this is a photo of now the dielectric. This is the high voltage cables. And so you would hook those up and that test gets done. Yeah. There's a table and this is what it looks like. And I've filled it out from the for the endoscopic video processing box. And so you don't know the diagram, but this basically betrays exactly what that diagram looked like, the insulation and voltages, and we needed to do these tests. And so here we'll specify no breakdown or breakdown. Yeah. And that's in table 883, which is the dielectric test method. And then the data results are in the end of the report there. This isn't the insulation table. It sure looks like it, right? But it's the dielectric values. And then the, you know, it's this table. But when we were doing insulation diagrams, I included the dielectric value with the creepage and clearance. But in the test report, there are two different tables. And sometimes in the test report, I'll have in the remarks, there's sort of a notes or a remarks column for the insulation diagram table. I'll put the dielectrics in there. So somebody looking at the beginning of the report can kind of see that in 883, there'll be these values. I think it's helpful, but it wouldn't be required.